Good morning, everyone. Thank you for being here, and thanks to the organizers for gathering all us together here. I'm very happy to attend this conference, and also thanks to the organizer for giving me the opportunity to talk about our work here. So today I will tell you something about mean convex, mean curvature flow in the Heisenberg group. This is the topic of a joint project with Gaia Bombardieri, who is here, and Mattia Fogagnolo, both of them from the University of Padova. It is an ongoing project, so today I am going to tell you some results that we already obtained, and actually some perspectives, some issues that you find in this problem that we find interesting and that we hope to study in the future. So we plan actually to study in the next weeks, in the next months. So to start with, I would like to tell you something about the mean curvature flow in Rn, in the classical setting, so in the Euclidean Rn. So I will try to write on the blackboard some basic facts so that you can, let me take another chalk, okay, so that you can read the basics on the blackboards throughout the talk. So the idea of a mean curvature flow is to study the evolution in time of shapes, which is somehow different from what at least I was used to do before, which is studying the shape of objects which do not depend on time. But actually in the next slide we will see that this may have some consequences also in the static study. Okay? And the idea of the mean curvature flow is the following. Take an initial surface, sigma 0, and you want to define a motion from this initial surface in such a way that the velocity vector is exactly the mean curvature vector, which is a vector pointing towards the direction of the inward unit normal, which is proportional to the mean curvature, the mean curvature which is positive on spheres, okay? So minus ht here on the slide is just minus ht, okay, is minus the divergence of the inner unit normal, which means that this quantity here without the minus is negative on spheres. So if you want to have positive curvature on spheres, here you're putting a minus ht. Okay, and so formally what you do is you define your initial surface as an immersion of a surface into Rn, and you want to define a family of, a one-parameter family of immersions from this sigma to Rn that solve the following differential problem. So you have that the velocity of the foliation at a point on the teeth evolved surface is just the mean curvature times the normal, okay? And you call sigma t the teeth evolved surface. So here is a picture of a possible mean curvature flow starting from this ellipse in R2. So let us go to some basic properties of this flow. So first property, perimeter decreases along the flow. So if you compute the first derivative with respect to time of the perimeter of your surfaces, here I am assuming everything is smooth for the moment, you see that this is decreasing, so it's negative, this derivative. And then second property, the first and easiest example that you can easily compute for this flow is the evolution of spheres. So if you start from a sphere, in Rn of radius r, then at time t, the evolution, so this is sigma 0, which is a sphere of radius r, then the evolution at time t will be a sphere of radius r squared minus 2t. And that's a computation that you can explicitly do. So this is r squared minus 2t. So in particular, this says two things. First thing, if you start from a sphere, your evolution is homothetical. So the teeth surface is obtained by dilating your initial surface. And second thing, you have finite time extinction in the sense that at time that annihilates this quantity here, so r squared over 2, you will get to a point, and after that, you will not have anything anymore. So you have finite time extinction of the flow. So, and as I was mentioning before, this is a time evolution study. So you study evolution in time. Sorry, okay. You study evolution in time of surfaces. But you can, for instance, use this flow to obtain some isoperimetric inequalities. You can study the flow throughout the final time and obtain some isoperimetric inequalities, for instance, in three-dimensional Riemannian manifolds. I'm not saying this is the easiest way to obtain those inequalities here. For instance, you can obtain Kleiner inequality, Euclidean isoperimetric inequality in three manifolds with non-positive sectional curvature. Again, I'm not saying that this is the easiest way to obtain this inequality, okay? But it's just to mention that at least in our end, there is some isoperimetric principle that may be connected to this flow, okay? And so this is actually our kind of starting motivation, because we wanted to see if there's any hope or any way to use this flow in order to study the isoperimetric problem in the Heisenberg group. And so we wanted to understand whether or not there are connections, for instance, with the conjectured isoperimetric sets in the Heisenberg group. And this is what I will tell you at the very end of the talk. So, okay, let us take a look at how things go in R2 and in R3. So in R2, actually, the flow is very explicit, very well understood. And it goes exactly like this. You can start from any, let me change because actually I'll go to the blackboard. Okay, so, okay, do you see it? You probably don't. Okay, so I'll go back here. If you start from any possible closed curve, even this very curly wire, the flow actually unrolls it, okay? It unrolls it in finite time till you get to a convex, so not a convex curve, a convex set in the plane. And once you get this convex set, then you shrink to a ball, basically. By this I mean that if you look at big time at dilations of your sigma t, of your shapes, for instance, dilations fixing the volumes, then you see that the shape converges to a circle in the plane. So any curve starts, it gets convex in finite time, and then it shrinks to a ball, and then it disappears in infinite time. So this is what happens in R2. Okay, again, this is a very deep theorem by Grayson, okay, in '87, so it's not obvious. Yes?
Is it true that this is not for curves that are C2, but still open for Lipschitz?
Yeah, actually that's the strong formulation. That's what happens in the strong formulation. So for Lipschitz curve, you cannot study the problem in the classical sense. You can use other formulations, which we will see later. And for those formulations, actually, I don't know if it's closed, the problem. I don't know if I answered. Good. So when you go to R3, things are quite different. So the first thing that one can think is that if you start from a convex shape, then it also shrinks to a ball, okay, in finite time. So it shrinks, it converges as a shape to a ball, and then it disappears in finite time. And this is what happens in a convex case. But if you go to non-convex starting initial shapes, then things may be very different. The first example of this, of this fact is this dumbbell, where you have here a thin tube connecting these spheres, two spheres. So when you start the evolution, in finite time, you will get to a singularity. So you will get to a situation in which the classical flow is not defined anymore, because at this point here, where the tube shrinks, you cannot define the curvature, the normal, okay? So you get to a singularity before the extinction time. But then actually people have been studying how to restart from singularities, and for instance, this is what happens to this flow. So the two balls disconnect, and then you shrink to 2 points, okay, to 2 disconnected points. But what is important to have in mind is that in the 3-dimensional flow, singularities appear before the extinction time, and this means that you actually need, before that, there is a classification of singularities in R3, so you know what can happen in R3. On the slide, you only find what can happen for convex or mean convex set, which I will tell you in a second what it means. But actually, let me tell you that generically, this is also what happens. For generic initial surfaces, this is also what happens, okay, in 3 dimensions. So this is a kind of a generic classification of possible singularities. So if you start from a convex set, we said you shrink to a ball, so the only possible singularity is a sphere, while if you start from a mean convex set, okay, let me say what mean convex means. If you start from a mean convex set, this just means that minus the curvature of, of sigma 0, okay, is positive, okay. Minus the curvature is, again, that's the curvature, the positive, the one which is positive on sphere, okay, sorry. That's the easiest way to set this problem, but it's confusing as names. But anyway, that only means that your curvature is positive on the initial surface. Let me mention that if you consider very thin tori, then these are also mean convex. So you don't have only spheres, you can also have thin tori, which turn out to be also mean convex. So the only 2 possible singularities are of this type. So you can only have spheres or these shapes, which are called the marriage rings, okay? I'm not sure I mentioned that already, but the pictures of these first slides are taken from a very nice paper, survey from Colding and Minicozzi on notices of the AMS, which I suggest you to read because it's very funny and enjoyable. Funny, I mean, it's enjoyable, let's say, okay? But this singularity, classification of singularity results needed a lot of attention. So this is a list of references for this problem. So it is very hard to classify singularities in general. But that's the situation in the 3-dimensional setting. So as I told you, you see singularities appearing and you maybe want to classify them. But anyway, they appear before extinction time. So what you need is to introduce some weak formulations for the flow in order to be able to run the evolution till the extinction time. And this has been done at least in two different directions. So first direction is a GMT direction, so the Bracke flow using varifolds. And then there's another formulation which is known as the level set method, which is the formulation that we will actually focus on. So this has been introduced in a numerical paper actually by Osher and Sethian, and then studied from the theoretical point of view by Evan Sprack and Chen Giga and Goto in 2 papers that appear in the very same issue of the Journal of Differential Geometry, so very same issue. And the formulation is the following. You assume, so this is, the level set formulation. You assume that your sigma 0 is the level set of a smooth function in our n. And you assume that also your evolved surfaces are level sets of smooth function depending on the position and on time, okay? And you rewrite this, classical strong formulation you rewrite this strong formulation for this type of shapes, and what you see is that this equation here translates into the equation that I wrote on the slide, which is the following. So it's dtu equals to gradient u, divergence of gradient u renormalized, and u of x and 0 is g of x. So you end up with a initial time problem for a suitable operator for a function defined on Rn. And this turns out to be a good operator to start to attack with viscosity solutions, because actually it is a degenerate elliptic operator, and you can see it reading the operator in this way. So if you rewrite this quantity here, it turns out that you get the Laplacian of u minus a quantity which is just the second fundamental form into the direction of the normal, okay? So you are removing to this Laplacian the one eigenvalue, okay? So to the trace of the second fundamental form, you are removing an eigenvalue, which means that then the first eigenvalue of this operator here is going to be 0, so it is elliptic in a degenerate sense. So that's why you can attack it by viscosity solutions. I'm not telling you what's a viscosity solution, it's just a weak formulation for a solution which uses continuity, which requires continuity of the functions instead of any other kind of differentiability. So the idea, this is what is done actually by Evans and Sprague, for instance, in the 91 paper, and the idea is just that you want to regularize this operator. If you rewrite this red operator here, you turn out with this operator without the delta square. If you add to this denominator the delta square, then you get to an elliptic operator. So you can solve the equation and then extract a limit for delta that goes to 0. Saying like this seems very easy. Actually, you need to play with barriers. It's not obvious, of course. It's in this paper by Evans and Sprague. But this is the way you can solve the problem and you can extract solutions. Let me also mention that since this evolution is geometric, when you find existence and uniqueness of solutions, you also want to have independence on the choice of your level set function g, and this is also what you can prove in the Euclidean setting. Okay, again, there's a special role for mean convex starting initial surface, because in this case, in the case of mean convex starting initial surface, so the level set method can be reformulated in a, say, stronger or easier way. Level set for mean convex. Okay. Instead of considering a function u, which depends on the position and on time, that gives you the level sets, so the surfaces, you are allowed to consider a function v only of the position and to look for evolved surfaces which are the t-th level set of your solution. So you are separating the variables in the mean convex case, and this gives you not anymore a degenerate parabolic problem, but a degenerate elliptic problem, so no dependence on time. So if you say that your initial surface is the boundary of an open-bounded set, then your boundary value problem is -1 equal to gradient u divergence of gradient u renormalized. And then that's a v. That's a v. And v of x equals to 0 for x on the boundary of omega. Okay? So in particular, this equation makes sense only if you are assuming this mean convexity, because using the equation, you see that the mean curvature, which is the divergence of the normal, if you use the equation, this mean curvature has a sign, which means that throughout the whole evolution, you will always preserve this mean convexity property, okay, of the flow. So all the surfaces are mean convex, and moreover, this problem tells you that in the mean convex case, you actually shrink inside your starting domain omega, because t is increasing, so v of x equal t is inside v of x equals 0, okay? So this is exactly a problem which is only well suited for the mean convex case. But in this case, you have some stronger type of uniqueness. So again, you find existence and uniqueness of solutions, viscosity solution to this problem, which means that you can use this problem to study the mean curvature flow in the mean convex case. But you get some stronger type of uniqueness, which basically passes throughout singularities. So you have uniqueness of the flow till the end, till the extinction time. And this is what is called also non-fat. So it has a relation with what is called non-fattening of the problem, which means that the evolved sigma t's don't fatten. So they are really level sets. So they are level sets because I defined like that. But they are, say, n-1 dimensional, okay? So this is the Euclidean situation. So we have strong formulation, ball shrinks to points, level set formulation in the parabolic setting, and level set formulation in the mean convex setting. So what we want to do is to study the Heisenberg setting, so the Heisenberg situation. Here is just the notation that I use for the Heisenberg group, so x1, x2, x3, and these are the two vector fields that generate the horizontal distribution. Okay. So let us start from a pseudo definition of the flow. By pseudo, I mean that actually this is not a definition that makes sense, but it helps us understanding what we want to do. So let us take a look at the strong formulation. You again start from an immersion F0, and then you want to define an evolution, so a family of immersions that simply, whose velocity is simply the horizontal mean curvature vector, okay? So you want to put an h here. You want to be proportional to the horizontal normal, and so the strength is the horizontal mean curvature. So here I am saying that the horizontal normal is just the projection of the Euclidean normal onto the distribution, and the horizontal curvature is the divergence of this vector, okay? But as you can immediately see, this has problems on characteristic points, because even if your surface is smooth, so in the Euclidean setting, starting from smooth surfaces allows you for this classical strong formulation. But in the Heisenberg group, so generically you will always have characteristic points on compact surfaces, which means that this formulation doesn't make sense even if you're assuming smoothness of the boundary. So that's why the mean curvature flow cannot be studied. Let me say, I cannot study it from a strong point of view, but it can be studied from a weaker point of view, so using viscosity solutions. So you redo exactly the same thing. You assume that your the starting surface is the level set, the zero level set of a function g, and then you assume that the evolved surfaces are zero level sets of your function u, and then it turns out that you only need to put an h on this equation, okay? No shock. You only need to put an h on this equation to study the level set formulation of the mean curvature flow. So let's take a look at this operator. This can be rewritten in this way. This is the horizontal Laplacian of your function u minus the horizontal Hessian computed onto the direction of the horizontal normal. So if this notation makes sense, this is kind of a degenerate subelliptic operator in the sense that it is the Laplacian minus one of its eigenvalues, okay? Compared to the Euclidean situation, so you don't have only the degeneracy given by the mean curvature flow, so the one that needed you to put a delta square at the denominator, but you also have the degeneracy of the sublaplacian itself. And so a way to study, to prove existence of solutions to this equation is to regularize the equation, both plugging a delta square here and approximating the sublaplacian with a suitable Riemannian approximation, okay? So epsilon is the parameter that I put in the Riemannian approximation, and delta is the parameter that I use for for the regularization, okay? And then you want to send epsilon and delta to 0 and to extract a solution of your original equation, okay? The one without epsilon and delta. And this is exactly what has been done by Caponi and Citti in 2009 to prove existence of solutions to the mean curvature flow in Carnot groups, actually, not only in the Heisenberg group. So I'm not sure I said it, but we are not the first who studied this problem, and this is a list of references. So there are at least 2 more groups of people which have been studying this problem. One of the groups is by Dragoni von Renesse, Dragoni Grande, who have been studying existence of mean curvature flow solutions by using some statistical methods, game theory, so game theoretical things. And then also Ferrari, Liu, and Manfredi used a different approach, but always with game theoretical arguments, okay? And let me also mention that a couple of days ago, actually, Citti, Dragoni, and Grande posted on the archive paper in which they do some numerical simulations for the mean curvature flow, which may be very useful, actually, to have simulations of our flow. So, okay, this is our equation, but let me go to an example, okay, that you can find on the paper by Ferrari, Liu, and Manfredi. So this is actually the only example of explicit evolution of horizontal mean curvature flow in the Heisenberg group. And it is the evolution of the Courant sphere. So this is just the level set of this function. This is connected to the fundamental solution of the sublaplacian, but it doesn't play a role actually in this evolution here. And let us observe that at characteristic points, which are these 2 points here, the North Pole and the South Pole, the mean curvature can be computed. So it can be computed as a limit, and it goes to 0 at characteristic points, okay? Let us stick with that. Then Ferrari, Liu, and Manfredi computed an explicit evolution of this flow. You have this expression, this U here. And what it turns out to be interesting that can be remarked is the following, is that if you compute the mean curvature at characteristic points of your evolved surfaces, it turns out to explode at characteristic point for any positive t. So you have instantaneous explosion of the mean curvature at any positive time, okay? This can be observed, and actually this is something that we will see at the end of the talk. Okay, another comment. So this is again the evolution. So you have finite extinction time again, because in order to have zeros of this function here, since all this quantity here is positive, you want this quantity here to be negative, which means that you're only allowed to find non-empty level sets for t, which is smaller than this quantity, okay? So after this time, the flow extinguished. But before that, you have this family of topological spheres. Yeah, so the pictures are in R2, but we are in R3. That's only to give an idea of what happens, okay? Okay, so let me skip this part. I will get back to that at the end if I have time. But let us stick with this example in mind. So you have this explicit evolution. Good. So let us go then to what we have done. So the study of the mean curvature flow in the mean convex case. So why studying the mean convex case? So first of all, that's because it has stronger properties, as we said. So it is described by a degenerate elliptic equation, okay? Which tells you that the whole evolution stays mean convex, and that you have a direction of the flow because it only shrinks. This is kind of the easy consideration. And then there are some non-trivial considerations on which I was very vague, but which tell you that under mean convex assumption, the mean curvature flow satisfies a stronger uniqueness that allows you to go till the end of the flow, so pass through singularities with a unique solution, okay? And then it will turn out that this is a good option to explore isoperimetric properties of the mean curvature flow, the horizontal mean curvature flow, and the existence of self-shrinkers, which are objects that are as the sphere in R3, they shrink homothetically. So the evolution is described by your initial surface by dilation. Okay, so formulation of the problem, no surprises. You only need to put an h. Of course, I'm saying you need to put an h, but it means that if you compute this strong formulation here, it turns out that this equation is satisfied. So the level set approach for mean convex set in the Heisenberg setting turns out to work like this. Again, so we want to define what, okay, let me go back a second. So assume that you have a solution of your flow, which is the t level set of a function v. So you have separation of variables. Then you compute this problem, and you take a look at what you need in order to have this problem well posed. And of course, you need to have a constant sign of the mean curvature, okay? Because the mean curvature is this quantity here. If you use the equation, it turns out to be positive, okay? Always positive. And this is what we want to call mean convex. So this is not exactly the assumption that we make in order to obtain existence. We need to make a different assumption to assume a slightly different thing, which is what we call strictly mean convexity in the approximated sense, and it is the following. So you say that a set omega is strictly mean convex in the approximated sense if you can approximate it, which is 0.3, L1 approximated, by smooth sets which are strongly mean convex in the Riemannian approximation. So it means that you have this omega epsilon whose boundary have strictly positive mean curvature in the Riemannian approximations, and this strictly positive mean curvature has a common lower bound which do not depend on epsilon, okay? So you have the mean curvature bigger than or equal to c for every epsilon. So this is the picture, okay? This is the picture. This is our final set omega, and you have some other objects omega epsilon, which turn out to approximate it in a good way. Okay. So the first question, which we are not, for the moment, able to solve is, do we have any, say, more geometric assumption ensuring this mean convexity in the approximated sense? And let me just mention that this is, and that the reason why this is not completely obvious can be seen, for instance, if you take a look at the Pansu set that I will introduce in a second, so not in a second, at the end. But if you take a look at the Pansu set, okay, which is not like this, but okay, this is the Pansu set, okay, Pansu sphere. So this has constant mean curvature in the Heisenberg group equals to 2 over the radius, okay, outside the characteristic set, okay. But if you compute the epsilon mean curvature of this, say, boundary of the Pansu set, let me call it PR, okay, Pansu set PR. If you compute the epsilon mean curvatures of this function, this goes to 0 at characteristic point. So it is not as easy as we hoped for at the beginning. It is not that if you have strictly mean curvature outside the characteristic set, then in the approximated sense, you have for free that the mean curvature is bounded away from 0 from below. So you really need to find another family of objects that well approximate your final shape. But so this is an open question, and if any of you has any suggestion that, or any will to work on that, we're very happy about that. So okay, that's our theorem, which I didn't read. But the theorem says take a smooth set omega. A smooth set means the boundary of your omega is a smooth surface that enjoys this strictly mean convexity in the approximated sense. Then you're able to find a viscosity solution to the mean convex formulation of the horizontal mean curvature flow that is also Lipschitz with respect to the CC distance, okay? So you have existence of solutions. How does this proof go? So we want to find solutions to this equation here that you can rewrite in this way. And you do exactly what I was mentioning before. You have to use epsilon as a Riemannian approximation parameter and delta as a regularization parameter. So the first step is to produce an estimate for a solution to this equation. This equation is an elliptic equation now, so you can, in a Riemannian manifold, so you can extract a solution and you can produce a bound for the gradient, the epsilon gradient of these solutions. This is basically done by maximum principle techniques. So you want to show that the maximum of the horizontal gradient, of the epsilon gradient, is attained at the boundary of your omega. And this is done again by maximum principle techniques, actually now reformulated also using a technique recently introduced by Pisante and Vecchi that smartly observe how to use the explicit computation of the Ricci tensor in the epsilon approximations in order to have that this constant C is independent on the parameters, okay? So once you have that, in a second step, so here I rewrote what you need to do in the first step. Once you have this first estimate done, what you need to do is to use the equation in order to produce an upper bound independent on epsilon for your epsilon gradient, so when you send delta to 0. And this, in the end, will allow you to send epsilon to 0, have convergence of the Riemannian quantities to the sub-Riemannian ones, and extract a viscosity solution to your Heisenberg, so sub-Riemannian equation. Okay, so this technique, this is to say that what you need to do is basically play with maximum principles. You can do it by studying barrier techniques, or you can use some different arguments by this Pisante and Vecchi paper, for instance, to have this kind of argument. Okay, so we have a solution of our mean curvature flow. Let us finally go to what was our motivation. Okay, let me recall what the Pansu shape is, what the Pansu surface is. The Pansu sphere is the boundary of the conjecture isoperimetric set, and it has, as I was mentioning before, constant mean curvature outside the characteristic set. So the question, more precisely, that we would like to address is the following. Is the Pansu sphere a self-shrinker for the mean curvature flow as the ball was in the Euclidean setting? So does it have this property that is the evolution is described homothetically rescaling the first initial surface? And what we, okay. First of all, we can apply our existence result to the Pansu sphere because of the fact, so as I was saying before, it is not obvious to find a family of surfaces that well approximate your Pansu sphere as the epsilon mean curvature goes to 0 at characteristic points. But luckily, there is a family of surfaces which are introduced by Tomter in '93, which well approximate the Pansu set in the sense that they are C2 sets in the Heisenberg Riemannian setting, having constant mean curvature on the whole surface that converge to the Pansu set. So we can apply our existence theorem to this setting. And what we found is that the Pansu set is not a self-shrinker. So it does not satisfy this self-shrinking property. Why? I want to tell you just a couple of things about the proof, because this will lead us to a consideration, to a more general consideration. So the idea is the following. You take your solution V, and you assume that the V induces a foliation by Pansu spheres, which means that sigma t is a Pansu sphere of a suitable radius RT for any positive t. This means that your V is actually defined as a one variable function f applied to this foliation by spheres. Okay, so your V is f composed the function that tells you what is the sphere that passes through the point x that you're fixing. Okay, and then here I am cheating because, as I told you, we are using viscosity solutions, so we don't really know that we can differentiate everything, but that's just the rough idea if the strong formulation could have been used, and this can be reformulated into the viscosity sense. But if you reread the mean curvature flow equation for this type of V, what you end up with is that f needs to satisfy this equation. So -1 is equal to f prime of r. This is a constant. We are going to stick to one leaf. So this f prime of r will be a constant times the gradient multiplied by the mean curvature. Okay. But as the mean curvature is constant, okay, at characteristic points, this goes to 0. Everything else is constant, so you will have -1 equals to 0, which is absurd. So the reason why it is not a self-shrinker is basically that it has characteristic points and bounded mean curvature outside the characteristic set. So we are not really using the structure of the Pansu sphere, but this gives us that Pansu spheres are not self-shrinkers. So, but as I told you, this actually says a bit more about this problem, because if you just assume that your mean convex level set solution is a foliation, so it is a function f defined on leaves that you assign, okay, you choose your favorite r, and you say at each leaf how much it's the value of this v by choosing a function f, then this equation needs to be satisfied. Again, in a weak sense, now I am saying the strong formulation, but in a weak sense, this equation needs to be satisfied, which tells you that at characteristic points, which are those points on which this gradient goes to 0, you need to have explosion of the mean curvature, okay? So in order to have an evolution, you need to satisfy that the mean curvature characteristic point immediately, instantaneously get infinite, okay? And this is actually comparable to the explicit evolution, the only explicit evolution that we have in this setting by Ferrari, Lui, and Manfredi that I recall here, where we observed that for positive time you always have explosion of the mean curvature. So, okay. Where does it lead us? So I have told you about yeah, sorry, actually I'll take one more mean. Yeah, okay, good. Okay, good, thank you. So I've told you that we have existence of solutions of this mean curvature flow, but now I haven't told you anything about uniqueness, because uniqueness actually is quite open also for the parabolic setting, due basically to the fact that in any surface you will have generically you will have characteristic points, and this poses a problem for the weak formulation, basically for uniqueness of the weak formulation. But so this is something that we would like to explore, and we actually expect that uniqueness holds for the mean convex mean curvature flow. But now let me go to this asymptotic behavior first. So let me go back to this example by Ferrari, Lui, and Manfredi, and for that I will actually thank Pierre Pansu, because yesterday made us realize that there was a different interpretation of what was written in Ferrari, Lui, and Manfredi's paper. Okay, so you have this explicit evolution, and you may want to see what happens when you send t to the final time. So what you can do is to define a dilation, okay, that goes to 0 for t approaching the final time, and you rescale your evolved surface sigma t by this quantity 1 over lambda square, okay, that explodes for t going to the final time. And what it turns out is that this rescaled set converges to a cylinder, okay? This is not what happened in the Euclidean setting. If you redo exactly the same for spheres, okay, or actually for any convex set, in the end, any rescaled surface will be a ball, okay, if you start from a convex set. But anyway, any rescaled surface is a compact set. While here, you are losing this compactness, so saying that you basically converge to cylinders. So what you may expect from this flow, and maybe Roberto told it a couple of years ago, but okay, now we have an idea of what it means. But so what you may expect from this flow is that starting from any surface, convex, for instance, mean convex, you will shrink to a line. You may expect this. So it's a completely different, you will shrink to a line, letting the mean curvature explode at characteristic points, okay? So whether or not you have self-shrinkers, of course, is open, but if this is true, then you don't have any self-shrinkers for the flow. Okay, I don't know if this is clear, but this is the idea. So, okay, this is what we expect then from the asymptotics, and this is what we aim to work on in the next weeks, in the next months, say. So as I was saying, to conclude, we also would like to explore mean convexity. As I told you, this mean convexity assumption that we made is in an approximated sense, but we would like to have some intrinsic formulation, so some intrinsic assumption that allows us to deduce this mean convexity, and this doesn't seem very obvious. And again, so the presence or not of self-shrinkers is open. So, and I think I'll stop here, and thank you for your attention.
Thank you. Are there any questions or comments? I have a question about the set of characteristics. Can we say something on the way it evolves along the flow of this set?
So we are basically not really able to track the evolution of points using the level set method. That's a global method, so we are not able to track the evolution of points. But of course, no, so we're not, for the moment, we are not able. I was up to say that if your surfaces are smooth enough, then the characteristic set is small. But I cannot tell you how it evolves.
Okay.
No.
Other questions or comments? Yes?
I'm wondering what is the relation of the mean convex and the aix-marseille?
Yeah, we don't know it yet. So we don't even know if Euclidean convexity implies the mean our notion of mean convexity, exactly due to this fact that, so basically being mean convex, H-convex, sorry, being H-convex means that this quantity here is positive, basically. But having this quantity positive doesn't imply that in the Riemannian approximation you're able to find sets whose mean curvature is bounded away from 0. Because this is false for the Pansu set. So what one would do in order to prove it is to actually let the mean curvature flow evolve. But then actually we have a problem because we need this as an assumption. So we really need to work it out in a different way.
Okay, others? No? So thank you again, Valentina.
Thank you.